So the net charge is determined by the pH of the medium, but it's also worth noting that proteins are amphoteric compounds. Amphoteric means that they have both positive charge and negative charge. You will see that one in biochemistry later. That is, they contain both acidic and basic residues. And the acidic has what? Positive charge, and the basic has negative charges. Each protein has its own characteristic charge or properties depending on the number and kinds of amino acids carrying amino or carboxyl groups. Nucleic acids, unlike proteins, are not amphoteric. They remain negative at any pH used for electrophoresis. So, like we said, proteins are amphoteric compounds. They are both positive and negative charge. They have both acidic and basic residues or segments or substituents or and each protein has its own characteristic charge properties depending on the number and kinds of amino acids carrying the amino or carboxyl group. You will understand this one when we do biochemistry proper. Suspended particles have an electric surface charge, which is strongly affected by surface adsorbed species. An applied external electric field thus exerts an electrostatic Coulomb force on the surface charge. Please ignore this. This is much more electricity. Ignore this. Ignore this one also. Okay, so this is talking about electricity charges. It's not necessary for Medilab students. Okay, so this is the consequence of buffer tank to hold buffer. Okay, so this is a schematic diagram representing electrophoresis, etc. These are different types of gel units. This is a gel tube. We put gel inside. This is a slab where you put the gel. So you can have a gel tube where you put the gel inside, or a slab where you put the gel. So polyacrylamide gel will be standing like this inside. Then agar gel, because it's organic and it's not strong, it will lie, this slab will lie down. Then the gel will flow horizontally. Whereas polyacrylamide gel, the slab will stand like this as it is, and the gel will be inside because it's very robust and synthetic. So these are different types of gel slabs, different types. So what are the applications of electrophoresis? In DNA and RNA analysis, a negative charge is applied so that proteins move towards a positive charge. Proteins are thus separated by size, density, and purity. Electrophoresis can provide, for instance, a DNA footprint to determine how proteins bind to DNA. So you guys in this class who will go and impregnate women and say that you are not the one, or you go and sleep with one woman and the lady will come and tell you that I'm pregnant the next day, and you say I'm not the one, I'm not the only one who has slept with you. We have to do DNA footprint or fingerprinting. Electrophoresis can also be used for plasmid analysis, which reveals mechanism by which bacteria become resistant to antibiotics in antibiotic production. We call this one biotechnology. Okay, so we end this lecture here. We are going to continue with the actual lecture, which is on hemoglobin electrophoresis, because that is what we will be doing in our hematology laboratory. Medical laboratory students, we do hemoglobin electrophoresis. That is, we look for hemoglobin A genotypes. A, we have the AS, the SC, so we can determine whether prospective suitors or people who want to marry, whether they can marry, or if they marry they will give birth to babies who are what do we call it, sickle cell. So we want to find out. So let's go to our next lecture. Let's do this hemoglobin electrophoresis. That is what is applicable in the medical lab. What I taught you initially is applicable in the industrial lab, like Noguchi Memorial Institute of Medical Research, like the Navrongo Research Center, and KCCR in Kumasi, KNUST, and all the research labs. They use the previous procedure I taught you. But here we are going to use cellulose acetate paper to separate hemoglobin in blood. That's why we call it hemoglobin electrophoresis. So let's begin. So let's look at the structure of hemoglobin molecule. So hemoglobin comprises two alpha globin chains, alpha 1 and alpha 2. This is the alpha globin chain. They are yellow colored. They are two. Then we have the blue or the ash color representing beta globin chains. So this is the actual molecular structure. We have iron, which is sequestered over here. This is the iron. And what is around this one, we call it the hem. And it's composed of porphyrin. You will learn that one later when you do hematology proper. Okay, so let's continue. Electrophoresis is a means of separating that's hemoglobin electrophoresis. Sorry, it should be hemoglobin electrophoresis. It's a means of separating hemoglobins. The first one is proteins and DNA, but this one is hemoglobin electrophoresis. So we separate hemoglobins. It depends on the migration of the hemoglobin molecules dissolved in a buffer or in a supporting medium when an electric current is passed through them. So initial one is protein separation, DNA separation, but this one is hemoglobin separation. Hemoglobin electrophoresis is a test that measures the different types of the oxygen carrying substance hemoglobin in blood. Why do we perform this test? This is because hemoglobin electrophoresis is performed to find out abnormal forms of hemoglobin. This procedure is termed hemoglobinopathy or hemoglobinopathy. Many different types of hemoglobin exist. The most common ones are hemoglobin A, hemoglobin A2, hemoglobin F, hemoglobin S, hemoglobin C, hemoglobin H, and hemoglobin M. Healthy adults only have significant levels of hemoglobin A and hemoglobin A2. That's healthy adults. So if you want a normal person who does not have sickle cell or these melanomas, these cancers or whatever, if you have a normal person who does not have any hemoglobinopathy, when we say hemoglobinopathy, anything pathy is what? Disease. So hemoglobinopathy, abnormalities. Okay, so healthy adults only have significant levels of hemoglobin A and hemoglobin A2. Some people may also have small amounts of hemoglobin F, which is the main type of hemoglobin in newborn babies. Certain diseases are associated with high hemoglobin F levels. When hemoglobin F is more than 2% of the total hemoglobin, then we say that the person has a disease. So hemoglobin F is called fetal hemoglobin. This is hemoglobin F. It's called fetal hemoglobin. So any fetus or when you are pregnant, after Beyond 2 months of pregnancy, we call the developing creature in the womb, we call that developing creature a fetus. Below 2 months in the womb, we call the developing creature an embryo. So 6 months, the fetus will have hemoglobin F, that is called fetal hemoglobin. And even up to 6 months after delivery, the fetus will still have this fetal hemoglobin, but in a lesser quantity. More than 6 months after delivery, still in the neonatal period, the fetus, the newborn baby will still be having this fetal hemoglobin, but in a reduced proportion. Hemoglobin S is an abnormal form of hemoglobin associated with sickle cell anemia. That is the problem. In people with this condition, the red blood cells have a crescent or sickle shape. These misformed cells then break down and can block small blood vessels. So this is how a sickled red blood cell looks like. This is a normal red blood cell, which is a biconcave shape. Then this is the sickled cells. Another example is this sickle cell, normal red blood cells. So as medical laboratory scientists, this is what you'll be seeing under the microscope. This is the sickling. It's like a sickle, the one we use to harvest rice. So the white people name it sickle cell. The cell has been sickled. So it's no longer the biconcave shape like this, but rather a sickled shape. So it blocks red blood cells. It blocks what? Blood vessels. You can see the sickle. It can even puncture the blood vessels. So you can even see over here clearly. So that's what we are talking about. Sickled cell. More diagrams here. Sickle cell. More diagrams. Sickle cell. So this is a sickle cell, and this is a normal red blood cell. More diagrams. Okay. So that's it. So you can see it blocking red blood vessels. Look at how they are collected here. Blood finds difficult to flow. And they are not able to distribute blood oxygen. They are not able to carry oxygen and food to the developing fetus or to the organs that need oxygen and nutrients, because they are blocking blood vessels. So in sickled cell guys, most of the time when they have the crisis, these sickle cells block the blood supply to the penis. So their penis become very, very erected. For maybe 3 or 4 days, you see that the penis will be erected. We call this priapism. Let me not waste time on sickle. Let's proceed. Okay, so like I said, as we continue, so hemoglobin S is an abnormal. Hemoglobin S is an abnormal form of hemoglobin associated with sickle cell anemia, and that in people with this condition, the red blood cells have a sickle or crescent or sickle shape. This, and I've shown you the shapes already. These misformed cells then break down or can block small blood vessels. Hemoglobin C is an abnormal form of hemoglobin associated with hemolytic anemia. Hemoglobin C is not as dangerous and serious as hemoglobin S. Okay, so let's look at normal values in the laboratory. Hemoglobin A1 is supposed to be 95% to 98%. Hemoglobin A2 is supposed to be 1.5% to 3.5%. In a normal adult, You shouldn't have more than 2% of fetal hemoglobin, because you are not a child, you are not a fetus, a baby in the womb, you are not. So you shouldn't have baby hemoglobin within you. So your fetal hemoglobin can be 0.8% to 2%, but not more than 2%. If you have more than 2%, it means that you have sickness, maybe cancer, leukemia, and the rest. So you shouldn't have more than 2%. Hemoglobin S is absent. Sickle cell in a normal adult is absent. Hemoglobin C is also absent. Well, let's look at infants or newborn babies. They are called infants. So for newborn babies and children, these hemoglobin molecules make up the following percentages of total hemoglobin. So let's see. We have for hemoglobin F in newborn, it's supposed to be 50% to 80%. Newborn, that's we call it, they are in the neonatal period. Okay, we call it neonate. So we have what? 50% to 80%. Then a baby who is 6 months will have only 8%. So this level, the level from 80% will drop to 8%. That's after 6 months of the baby's life. Then after 6 months to maybe over 6 months, that's 1 year going, it will drop from 8% to 1%, or between 1% to 2%. The presence of significant levels of abnormal hemoglobins may indicate hemoglobin C disease. If you have these abnormal levels of hemoglobin in your blood, then you have what? Hemoglobin C disease, or sickle cell anemia, or rare hemoglobinopathy. Hemoglobinopathy of unknown cause or etiology. We have two different types of hemoglobin electrophoresis. We have the cellulose acetate electrophoresis, that's the alkaline pH. The buffer has an alkaline pH, or the buffer is a basic buffer. Then citrate agar electrophoresis, the buffer is an acid buffer. It has an acidic pH. That's why we have citrate. You know, citrate is what? A weak acid. Cellulose acetate is a weak base. So cellulose acetate and at alkaline pH. So cellulose acetate, let's look at cellulose acetate electrophoresis. Cellulose acetate hemoglobin electrophoresis at alkaline pH is the primary screening procedure used to detect variant or abnormal hemoglobins, of which there are several hundreds. Hemoglobin is made up of heme and globin, and is identified according to the structure of the globin chains. Abnormal globin chain is the what? The proteins, the alpha 1, alpha 2, or beta 1, beta 2 proteins, and they do the separation in hemoglobin electrophoresis. Abnormal globin chains will differ in the number, type, and sequence of amino acids. This gives the HB its identity. The major portion of normal adult HB is A. That's the normal. So the cellulose acetate at alkaline pH, that's what we use for normal screening in the laboratories, in the hospital labs, and every lab that does hemoglobin electrophoresis to determine hemoglobin genotype. We use the cellulose acetate hemoglobin electrophoresis setup. That's the first line. So in addition, up to 3.5% hemoglobin A2 is normally present, along with less than 2% hemoglobin or fetal hemoglobin in a normal person. The more common mutant hemoglobins are hemoglobin S, hemoglobin C, hemoglobin E, hemoglobin G, hemoglobin J, and the laboratory hemoglobin. So see, all these are abnormal hemoglobins. When an abnormal hemoglobin is detected on cellulose acetate electrophoresis at an alkaline pH, that is the alkaline pH, the basic pH is between 8.2 to 8.6. Further testing is frequently indicated. We do further tests for hemoglobin S, quantitation of hemoglobin A2 and hemoglobin F, citrate agar gel, acid or alkaline globin chain, or neutral pH electrophoresis may also be indicated. What's the principle behind electrophoresis? Electrophoresis is the movement of charged particles like what I showed you in the previous lecture in an electric field. In an alkaline pH, Hb is a negatively charged molecule and will migrate toward the positive anode. So hemoglobin is negatively charged, you have to know this, at an alkaline pH. So negative will be attracted towards the positive charge pole. The various hemoglobins moves at different rates depending on their net negative charge, which in turn is controlled by composition, amino acids of the amino acids side chains. They determine whether a protein is or an amino acid is positively charged or negative charged. The red cell hemolysates or red blood cell membranes are destroyed to free the hemoglobin molecules for testing. Before you want to test, you have to hemolyze the red blood cells. So when hemolysis is the breakdown of the walls of the red blood cells to release its content. So we need the hemoglobin, the globin chains. So it's placed in a cellulose acetate membrane, which is positioned in an electrophoresis tray with inoculated hemolyzate near the cathode. Continuation. One end of the cellulose acetate strip is immersed in the buffer, which is at an alkaline pH, on the cathode. So we use, instead of us using a gel over here, we use a cellulose acetate paper or strip. And we immerse this paper on the cathode side, and the other end is also placed in the buffer on the anode side. I will show you this one shortly. So let's see this. Let's see this illustration. Let's see this illustration. Let's see this illustration. Let's see this illustration. This is a cellulose acetate electrophoresis. So we can see the paper. One is placed on the, this is the anode, the positive charge, this is the negative charge. The paper is placed in one of the wells, in one of the buffers, then the other side is placed in the other buffer. So when we put the specimen here or here, it will move towards the end. So we can see another one is here. It has been put in the well or in the buffer. So migration takes place. You can see the blood moving and to form a band here, different bands. So you can see this is cellulose acetate. You can see the migration of the proteins or of the globin chains moving. This where the origin, where it starts from. Then it will go to the end. So those molecules who have smaller size, are heavy weight, they will move last. They will last. This is a control band. This is the control band or the ladder, molecular ladder. So molecules which are of heavy weight will lag behind. Those lighter weight molecules will move faster. So you can see them moving faster. So this one is lighter than this. This is lighter than this. This is lighter than this. So that's how it's displayed. So when you go to the regional hospital laboratory, this is what you'll be seeing. So we don't need any staining because the blood itself is red. So we have the control. These are the samples: 1, 2, 3, 4, 6, 7, 8. So this is the first one. It's a control, so it will move. This is the second one. That's the patient, so the band. So if the control band is showing here, patient band is showing here, this is A, then that means the patient is A. If the patient 2, okay, so patient 2, we have what? One band here, one band here. So if this is A and this is S, and we have the patient is one here corresponding to the control and another one corresponding to this control, then this patient is AS. This number 7 patient is also AS. But if you see only one band, that's patient 4, only one band, it means that it's AA, and they're on the same line. So you compare, use the control band, the proteins that have been separated on the control ladder to match or identify the proteins or the type of genotypes in the patient's samples. So as previously shown, one end of the cellulose acetate strip is immersed in the buffer at an alkaline pH on the cathode side, and the other end is placed in the buffer on the anode side. An electric current of specific voltage is allowed to run for a time period. During electrophoresis, the Hb molecules migrate toward the anode because of their negative charge. The difference in the net charge of the Hb molecule determines its mobility and manifests itself by the speed with which it migrates to the positive pole. Examples of fast HBs are hemoglobin baths. They are faster because they are lightweight, and the two faster variants, hemoglobin H and hemoglobin I. The cellulose acetate membrane is then stained in order to some stain the cellulose acetate membrane, but we at Regional Hospital we do not stain. None of the medical labs in Ghana stain the cellulose acetate paper because the blood itself is colored. By noting the distance each HB has migrated and comparing this distance with the migration distance of known controls, like what I showed you in the images, the types of hemoglobins may be identified. So this is a setup. Okay, so we have the buffer, the wick, it supports the gel slab. This is a gel. This is not a paper, it's a gel. Just to illustrate to you. So sample wells in gel. So this is the sample well. This is where we put the sample 1, 2, 3, 4. So this one has 4 sample wells. So 4 samples should be put. 1 is supposed to be a control, and the 3 are patient samples. This is the power source we connect to. Red wire to the red black wire to the black. This is the positive anode and the negative cathode. They supply the electrical field. So we have the electrophoresis setup using citrate agar. And citrate agar, the first one is cellulose acetate paper. The next one is the citrate agar. Agar is like a gel. It's like a gel. So citrate agar separates hemoglobin fractions that migrate together on cellulose acetate agar. So after doing the cellulose acetate electrophoresis, you now look at the citrate. You want to verify whether what you had in the cellulose acetate paper is correct. So you use the citrate. You now use the citrate agar to separate the components you separated with cellulose acetate. So all HB specimens that show an abnormal electrophoretic pattern in alkaline alkaline media, cellulose acetate agar, should undergo electrophoresis on an acid citrate agar for verification. Citrate agar electrophoresis is used to confirm variant hemoglobins and further differentiate hemoglobin S from hemoglobin D and G and hemoglobin C from hemoglobin E and the rest. The procedure should not be used as a screening procedure because many abnormal hemoglobins migrate with hemoglobin A. Yes, the only screening procedure is the cellulose acetate in alkaline media. You cannot use this citrate agar. And using even citrate agar for screening, it's very expensive. Citrate agar is expensive to buy. So we can't use it to screen. Screening is like you go to a lab and say, I want to screen hepatitis B, I want to screen HIV, then they'll do a 10 CD or 5 CD test for you. It's different from confirmation test which you do PCR. So the citrate agar electrophoresis setup is like a confirmation test for hemoglobin electrophoresis. However, this process is the method of choice when examining newborns with cord blood specimen, that's blood from the umbilical cord, and infants under 3 months of age. For some abnormal hemoglobin such as hemoglobin S and hemoglobin C, because the test is able to detect quantities of hemoglobin not easily seen by other techniques. That's good. So this is an example. So we can see for a normal patient, using the migration, this is the origin. So the specimen will move from here. So this hemoglobin A2, fetal hemoglobin. So you can say hemoglobin A2 is heavier than fetal hemoglobin, which is also heavier than hemoglobin A. Okay, so let's see. For beta thalassemia trait, hemoglobin A2 appears thicker, meaning that there's more of the hemoglobin there. Then the hemoglobin A also is there. But the fetal hemoglobin is at a very small proportion. So this one can be 20% of the hemoglobin A2. Then the hemoglobin A can be about 70%. And the fetal hemoglobin can be about 1.8 or even 0.5% less. But still there is fetal hemoglobin there. Beta thalassemia major has hemoglobin A2 as small as the beta thalassemia trait. Trait means a carrier, and the major means the disease itself. So for the beta thalassemia major, there is significant or high proportion of hemoglobin F, meaning that if you have beta thalassemia, which is common in Tamale and Italy and the rest, it's common in Tamale and Italy. You can see more. You see that an adult is walking around, but he has a fetus or a baby in the womb, hemoglobin inside him. So that person is sick, and they are prone to anemias. Anemia means that your hemoglobin is less than 11. So you are anemic, you don't have blood, you need blood, you are short of blood. So beta thalassemia patients have a higher percentage of fetal hemoglobin. For the sickle cell trait, those who are carriers, we call them traits. We have more of the hemoglobin S and more of the hemoglobin A. But if hemoglobin A is 70%, then hemoglobin S is about, if hemoglobin A is, let's say, 50%, hemoglobin S is about 40%, and the rest is hemoglobin A2, which is 10%. For the sickle cell anemia itself, hemoglobin S is more than hemoglobin F. So there is fetal hemoglobin there, there's hemoglobin A2, but they don't have hemoglobin A. That is a normal hemoglobin. So these people are prone to hemolytic crisis. Small time they need blood, small time they are fainting, and they don't even live up to their normal lifespan. So this is another electrophoregram, hemoglobin So go through and see whether you understand it. So this is we have results 1, 2, and 3 for patient 1, 2, and 3. This patient has only, if it is AA, then it's AA. This patient had 2 bands, 1 band here, 1 band here. So this patient can be AS or anything. This patient has also 2 bands. So, but this is a separation. This is just an example. So 2 bands here. The third one is not clear. So look at the proportion. These are the peaks. So 70%, you see the peak is very long. It means that higher concentration. So we have higher concentration. So you can see the blue color over here is thick. Here 17.3% is very small. The blue color is not long. 12.7%, blue color is short. So you can see hemoglobin S trait, that's a carrier. The carrier has the A2, this level. Hemoglobin C trait also has the same concentration of the A2. So this is how we end the class. So this, I'll forward this lecture notes to you because this is what you'll be doing next week. Biophysics, next week Friday. So make sure you read it so that next week Friday I'll come to class and explain whatever you've read. Thank you very much, and may God be with you.